Hello and welcome to Mr. Linford's math course. In today's presentation, we're going to be discussing an introduction to polynomials. In particular, we're going to review what a polynomial is and how it can be defined. We're also going to go over specific types of polynomials and some vocabulary around the components of a polynomial. Now first, we should go ahead and define what a polynomial is. A polynomial is a finite sum of terms that are of the form a times x to the n power, where a is a real number and n is a part of the natural numbers. Let's dissect this definition a little bit. We are saying that a polynomial is a finite sum of terms. Finite, remember, that's the opposite of infinite. We're adding up a bunch of terms, but a finite number. We're not adding up infinitely many terms. Okay, we're just adding up some number of terms, and those terms are of this form, a times x to the n power. Now you're saying, well, what is this form really? Remember, a is a real number and n is a natural number. Now the real numbers, those are any number on the number line. Maybe I should write that down for us. The real numbers are any number on number line, and the natural numbers are, well, they're sometimes written as z, maybe I'll write it down here. They're sometimes written as the z positive or the z greater than or equal to 0. Basically what that just means is the natural numbers are positive. They're positive integers, or you could think of them as positive whole numbers. Those are the natural numbers. They're also called the counting numbers, right? 0, 1, 2, 3, 4, and 5. So a polynomial is really just an algebraic expression. You're adding up a bunch of terms, but these terms have to be in a specific format. There is a general form to this that a lot of textbooks use when defining a polynomial. They'll say it's an expression of this format. We can kind of see how this form is similar, really, or reflecting the definition that we just went over. First off, you're adding a bunch of terms here that are of the same format, right? You have some a times of the variable x to some whole number exponent. You have to keep in mind here that all of these a's, a to the n minus 1, a to the n minus 2, all the way down to a to the second, a to the first, a to the 0. These are all just real numbers. These are your coefficients. They're any number on the number line. For example, let's go ahead and pretend we have the number, I don't know, let's just say 5. 5, that's our real number, and then we're going to multiply that by the variable x to some exponent. All right, 5 times x to the 7th power. This is one of the terms to a polynomial. We have a real number coefficient, and we have a natural number exponent. A natural number, or a whole number that's an integer, right? A positive whole number. That is our exponent. So this is the form that we want. We have real number times x to a whole number power. What's another example we could do? Let's take 1/2 times x to the 4th. This is also a term that we can use, right? A half, that's a real number. It's on the number line. And 4 here is a natural number because it's a positive whole number. We could even have a coefficient that's something like pi times x to the 5th power. Because pi is a real number, and 5 here is in fact a natural number, so this term would work as well. What I hope you're understanding here is that the polynomial, as long as it fits this format of some real number times x to some whole number power, it works. It can be a term that we're adding into the polynomial. Now, in the form that we have here, you'll notice that the polynomial is arranged in a very specific way. Notice that the exponents always drop by 1 every time. So the thing with polynomials is that we write them in what's called descending order, okay? Descending order meaning we drop their exponents. So descending order. Let's say I had the terms 2x squared plus 7x to the fifth minus 4x to the first. If I wanted to work with this, first off, is it a polynomial? Well, yes, it is. We have real number times x to a whole number power, real number times x to a whole number power, and same thing here. If I wanted to write this in descending order, I would have to start with what's the largest term, what's the term that has the largest exponent? And that would be 7x to the fifth. So I take 7x to the fifth, and then I'm going to write the next largest exponent. And the term that has the next largest exponent is 2x squared. So I'm going to add the 2x squared, and then the last one is the minus 4x to the first. So minus 4x. This is how we are going to write polynomials. We want to make sure, one, that we have the proper format, right? We'll make sure we're having the terms in the form that we need. But then we should really make sure that we're writing this in descending order. We'll see later on, especially when you get into more advanced algebra, there's a lot of information you get told about for the function based on things like its highest exponent and its leading terms. So this is the idea of the form that we want things, and we want it in descending order. Let's try another example, this time where we have something like, let's say, negative 3x to the seventh plus 6x to the 10th minus, oh gosh, I don't know, 5, whatever. Let's throw in a regular number in this time. Well, notice that this term doesn't have an x in it. So would we say that this is a polynomial because it's just got a regular coefficient in it? We would say this is still a polynomial because, yes, this term is missing an x. Take a look at this form here. We can go all the way down to x to the 0 power. What's anything to the 0 power? It's just 1. So we can get rid of that. So we are allowed in polynomials to have one constant term, one term that just stands alone, okay? We're allowed to have one term that doesn't have an x to it, one constant term, as we call it. So if we're going to put this in descending order, we need to start with the highest exponent on x, that is 6x to the 10th. The next highest exponent is the x to the 7th, so we're going to subtract 3x to the 7th, and then I'll subtract 5 as the last thing. You'll notice, based on the general form here, that the last number is always the standard number, okay? It's just the constant term. So again, here we have an example of writing a polynomial in descending order. With the idea of polynomials defined, what I'd like to do now is take some time to describe some different types of polynomials. We often categorize polynomials by the amount of terms that we have. For example, you can have a polynomial that's only one term. We call that a monomial. This is a single term polynomial. And when I say a single term, I mean we have one of those terms where it's a real number times x to some whole number power. So let's say, for example, let's say 7 times x to the third. Here we have a real number times x to a whole number power, and this is the only term in the polynomial. We're not adding any other terms to this. And this is allowed. This is a type of polynomial. I know it seems kind of contradictory. We have a polynomial where there's only one term, but this is allowed. We call this a monomial, the root word here being mono, singular. And you can have really any term that you want, as long as you have a real number to begin with, and then you have it times x to some whole number power. Let's say this power would be, I don't know, 10. Would this count? What if I just had the number 5? Would this be allowed as a monomial? Well, hopefully you're saying yes, it would, because this is a term that we can have for a polynomial. Remember, this is like saying 5 times x to the 0 power. And what's x to the 0 power? That's just 1. We are allowed to have just standard standalone numbers. Regular numbers are also polynomials. This is allowed. This is a monomial. So that's the idea of a monomial. A binomial, similar to a monomial, we look at its root word, bi, meaning 2. A binomial is a 2-term polynomial. I'll just abbreviate that poly. So a 2-term polynomial is where, again, we're only adding 2 terms together. So something like x plus 2. There are 2 terms that we could have. We could have the variable x with the 1 coefficient and 1 exponent. And we could have the number 2, that's like 2 times x to the 0 power. Okay, so that's a polynomial. We could have things more complicated like 7 times x to the 51st minus 0.37 times x to the 3rd, whatever. As long as there are just 2 terms we're combining together, then we have a binomial. And again, the trinomial, like before, we look at the root word tri, and we see that we would have a 3-term polynomial. A 3-term polynomial. Again, we're now just adding 3 terms together. Some common examples of that you'll see include something like, let's say x squared plus 2x, so if I can write that neater, x squared plus 2x plus 1, 5x squared plus 7x minus 3, even something more complicated like, square root 3 times x to the 7th minus 5.2 x to the 3rd plus pi x squared. This is a polynomial as well. Keep in mind, we haven't done an example like this, but roots are square root of 3 irrational numbers, just like pi. They are in fact real numbers. They exist on the number line. So we can have those as our coefficients. So all of these terms, these 3 terms are combined together. They all fit the definition of what the term should be. And we've combined them together so by addition or subtraction, so that way we have a polynomial. More specifically, a trinomial. Now, you, of course, can have 4-term polynomials, 5-term, 6-term, 7-term, 8-term, whatever. The most common types that we're going to work with are these 3, monomial, binomial, trinomial. Anything after that, we stop giving them really a name. We just say a 4-term polynomial, a 5-term, a 6-term. Now, we don't just really define a polynomial by the number of terms that there are. Now, we want to know the number of terms because this will have something to do later on with really the complexity of the graph, I would say. The more terms that you have, the more complicated the graph can become. And really, we want to know how many terms there are because if we want to, a big application of polynomials is being able to model data, to model graphs. And the more terms that we have, the better able we are to do that. So that's why I say your graph gets more complicated the more terms that you add to it. It's able to bend more to different curves and go off to different directions. So you can really change the range quite a lot by the more terms you add to it. However, we don't always just describe polynomials by the number of terms that there are. We also describe them by their different characteristics. What I'd like to do now is take a look at an example of a polynomial and identify some key components to the polynomial, go over some vocab terms that we'll use. For example, look at this polynomial here. 5x squared plus 3x plus 2. This is a trinomial, but we have other ways of describing it in more detail. First up, one of the big things that we want to talk about whenever we talk about a polynomial is its leading term. The leading term is the term with the largest exponent on x. The term that has the largest exponent on the x variable. Well, which one is that? 5x squared. That's the one that has the largest or highest exponent for x. Now, we call it the leading term because when written in descending order, it is the first, let me write that a little neater. It is the first term to the polynomial. So that's why we call it the leading term. So here it is 5x squared. Now the leading coefficient, just like the name implies, is the coefficient of the leading term. The coefficient of the leading term. So for us here, it would be the number 5. That's the coefficient of the leading term, 5x squared. Now the degree of the polynomial, this is a very important vocab term to get down and to remember. It's not as intuitive as the others, but the degree of the polynomial is the largest exponent, on x. The degree of the polynomial is the highest exponent that x achieves. So take a look in this example, that's 2. That's the largest exponent on any of the x variables. It's also the exponent for the value in the leading term. So for us, the degree of this polynomial is 2. We would say this is a second degree polynomial. Now, these definitions to us, they're really just simple vocab terms right now, but we will use them later on, especially in intermediate algebra and algebra 2, when you start talking about different types of polynomials and the graphs of them. You'll realize that the degree of the polynomial tells you a lot of information. In particular, it tells you information about the shape of the graph. And the leading coefficient really tells you a lot about the dimensions to the size of the graph. So these are some things to keep in mind as we start working through different types of polynomials and how we can go ahead and interpret them. Now, that's all that I have for our little introduction here. Hopefully it's making sense to you. And really, hopefully you're grasping what the definition of a polynomial is, so what's allowed to be a polynomial and what's not allowed to be a polynomial. But if you do have any questions or comments, feel free to contact me. My email is klinford, that's KLINFORD, @wccnet.edu. Let me know what you thought of the video, if you have any questions or comments, and until next time, take care.